It is widely assumed that Einstein's general theory of relativity cannot be combined with quantum theory. At least, so far, nobody has found a truly conclusive way. In this presentation it will be shown that the job was in principle already done by no other than the German mathematician David Hilbert, and that there is no need to combine quantum theory and general theory of relativity, because the latter already contains the first. A theory of everything, for which we are aiming here, should not only contain Einstein's general theory of relativity, but also all major quantum equations, and it should also explain the appearance of what we describe as matter. In this presentation, we will concentrate on the metric derivation of so-called particles at rest. Here we show the spinor presentation of such a particle in Dirac style. But we point out that our interest lays not in the explicit derivation of the spinor solution requiring the Dirac equation, for this we refer to part 3 of our video series, but only in the metric origin of the exponential part of these classical particle solutions. Our starting point is the so-called Einstein-Hilbert action, a variational integral based on a Hamilton extremal principle. Already in 1915, it was the German mathematician David Hilbert who derived Einstein's field equations from such a fundamental minimum principle. What Hilbert apparently did not see was that his formula in fact contained much more than just the Einstein field equations, but that he had also found the fundament for quantum theory. In this presentation, we will now show what Hilbert had missed, or, taking Hilbert's genius, simply not considered important enough to be mentioned at all. As we have already shown in an earlier presentation, see part 1 of this series, that we do not need the matter term Lm nor a cosmological constant to obtain matter, we set both lambda and Lm equal to 0 and just proceed with the curvature of spacetime, known as the Ricci scalar, as the kernel within our variation. Now, by following Hilbert's classical derivation, we obtain the so-called vacuum Einstein field equations. Things change, however, in a rather interesting manner when introducing a slightly adapted metric tensor with a scaling factor as shown here. Hilbert's variation then yields a much more complex kernel. Please note that this kernel can dramatically be simplified by demanding the scaling function to fulfill a special condition. We treated this path in our second part of the series, where we derived the metric, which is to say generally the quantum relativistic Klein-Gordon equation. From here now we could simply repeat our evaluation with respect to the Klein-Gordon equation, see our corresponding previous presentation on this matter in part 2, and then apply Dirac's strategy to factorize the Klein-Gordon equation. This, however, will only lead us to the classical Dirac form and hence the classical particle at rest solution. We are aiming, however, for a metric generalized solution in order to see how curvature and other dimensions act within the new, wider theory. Thus, we will avoid a simple condition for f shown here and proceed as follows. At first, we split up the variated contravariant metric tensor into its scaling and its tensor part as shown here. As a result, we obtain two equations, a scalar and a tensor one. For the time being, we ignore the tensor equation, for example by simply assuming that the variation of the metric tensor gives 0. Then we intend to fulfill the scalar, which is to say the first equation, by demanding the kernel of the integral to be equal to 0. This gives us the following partial differential equation, and by inserting a clever condition for the scaling function f, we obtain an equation where for every number of dimensions the flat space solution, which is to say r equals 0, plus the particle at rest assumption, the result would be the classical Dirac style particle, just without the spinor part, which we here do not consider. Our problem is, however, that this solution must be fed into the function capital F, and due to the original condition being used earlier in our derivation, we end up with a complete solution being anything but of the classical particle addressed style. So we ask ourselves, which one of the conditions we have set may have caused this trouble? It could be r equals 0, f solely depending on t, or our assumption that the metric tensor does not depend on t, or, naturally, our setting for the function capital F. Here, in order to shorten things, we only consider the r equals 0 condition and leave all other settings as they were. This, namely, changes the differential equation with respect to f, t, as follows, and subsequently also gives us a much more useful total solution for our capital F of f. As before, we have two solutions, but the usual matter-antimatter symmetry, as known from the classical Dirac solution, has vanished. We immediately see that this time the exponential terms are not neutralized by the logarithm in our function capital F. In fact, for negative r, we obtain very interesting patterns of oscillations. Here the figure shows one example in a four-dimensional space-time. While the blue line shows the real part of our scaling wave function for both solutions, we have the imaginary parts for the first solution, yellow, and the second solution, green. Unfortunately, we obtain only reasonable, which is to say oscillating, and thus particle solutions for negative Ricci curvature. In other words, we would not obtain particles, at least not particles at rest, for truly flat spacetimes with Ricci tensors and Ricci scalars being 0. Thereby, we do not count the volumetric scaling as part of the metric, but as an additional feature which fills Einstein's general theory of relativity with the long-sought quantum effects in quite a comfortable way. However, when going back to our extended, which is to say scale-factored Hilbert variational integral, and bringing the tensor and the scaling part back together, we suddenly see that even in a completely flat spacetime, meaning where all r terms are vanishing, we can still have a scalar equivalent for our r in order to, hopefully, obtain the necessary particle at rest condition. We only need to remind ourselves that the tensor part under the integral has to be summed up with the contravariant variated metric tensor, and this just gives a scalar again. Just a bit of definition and reordering, plus our preferred setting for the scaling function, and we are comfortably back with the right equation for the metric creation of particles. For completeness only, we here also give the unabridged form of this equation. By inserting what we know about our scaling function capital F, we end up with an equation completely depending on the inner wave function f, its variation, and the variation of the contravariant metric tensor. It should be pointed out, however, that there are also other options to metrically derive masses and potentials via additional dimensions. The interested reader may find more information in the books shown here or other publications of this author. We explicitly want to point out, however, that we do not consider us the first who have found the connection. In principle, namely, it all was already inside Hilbert's ingenious approach, and he only could not see it because at the time he wrote down his equation, the fundamental equations of quantum theory were not yet discovered, and furthermore his main goal was the derivation of the Einstein field equations, and thus, as Einstein had not bothered about also finding quantum equations inside his general theory of relativity, Hilbert, as a mathematician, obviously saw no need to consider the broader spectrum residing in his approach. These new insights open up a variety of possibilities for the most astounding developments, be it inexhaustible sources of energy, future weaponry, metric artificial intelligence, quantum gravity computing, or completely new, and what is much more important, truly unbiased and most holistic modeling tools for almost all sorts of problems. And how could such developments be realized? Well, the optimum, of course, is the global approach aiming for the quantum gravity computer and naturalized AI, which is a Manhattan-sized project. How this disrupts everything and makes the owner the global monopoly to just everything can be extracted from the material presented in this talk. A next smaller step is just the naturalized AI, which still is a small Manhattan project. This too already reaches very far and propels the owner into a global monopolistic and long-time leading position, unless somebody achieves a takeover via a working quantum gravity computer tech. And finally, everything else are just service projects.